Okay, chapter 6 is where all of this stuff comes together that we've been working through most of the semester. And to begin, we have to lay out what a vector field is and talk about how to sketch those vector fields. Sketching isn't super important in the real world, but sketching is very important to bringing the concept into your head. What is a vector field? Essentially, it's a function that attaches a vector to every point in space. So here's a point, here's a direction and a magnitude. Here's another point, here's another direction and a magnitude. And imagine a function that erects a vector at every point in three-dimensional space. Or we can have two-dimensional vector fields where at every point in two-dimensional space there's a two-dimensional vector. We're going to restrict our attention to vector fields of the same dimension. So we're going to look at two-dimensional vector fields where at every point in the plane we're attaching a 2D vector, or three-dimensional vector fields where at every point in space we're attaching a 3D vector. There are other mixes and matches of that kind of thing. You can have a five-dimensional space with three-dimensional vectors attached at every point. We're not doing that here. What are you responsible for here? Mostly, again, just to get the concept of what a vector field is. And we're also going to talk a little bit about the relationship between certain kinds of vector fields and level curves. And we're going to talk about a very special kind of vector field, the vector field that is essentially the gradient of some function. Remember that when you take the gradient of a scalar function f, you get the vector that is the partial of f with respect to x, partial of f with respect to y, partial of f with respect to z. You get this three-dimensional vector. That's a vector field. It turns out to have really special properties, properties that we'll explore extensively in the coming sections. They're very special vector fields. They occur in physics and engineering. They occur naturally in the context of gravitation, electromagnetic fields. So very, very important class of vector fields, the conservative vector fields. So examples of vector fields. I love vector fields. They're extremely visual. You've seen me with my own vector field in lots of examples throughout the semester. Let me get my vector field up here. So this is a highly stylized vector field, but it is a vector field nonetheless. It's a two-dimensional vector field, and I can change the function that's in the first coordinate and change the function in the second coordinate and get a variety of vector fields. I would encourage you to go visit this link and play around with this two-dimensional vector field visualizer. It's important to note that, again, this is a highly stylized visualization. There's no motion in this vector field. What you're seeing here is sort of what it would be like for particles to move within the vector field, but the vector field itself is static. In this particular case, the vector field is always pointing away from the origin, but I could change it and make it sort of circular if I put -y here and x here and then click update the field. Now I've got a circular field. Again, this is a static field, but what we're seeing is how particles would move if they were inside of this flow. All right, back to the section. So you get a lot of beautiful diagrams here. This is, I don't know what this is. This is gravitational field between the Earth and the Moon, I guess. This is fluid flow in a stream. We've talked a lot about that this semester. The book sort of splits up vector fields into two-dimensional vector fields and three-dimensional vector fields. I'm not super excited about that. I think it's just the same idea, and it doesn't really need to be cut up so finely. That said, I want you to look in R2, I want you to think about how to sketch these things, and there's a couple of examples of how to draw vector fields in two dimensions. I'll leave that to you. I'm actually going to do a specific example in the exercises at the end here. The book also talks about sketching vector fields in 3 dimensions. Please don't bother with that. That's why we have computers. I think you're going to get the concept of what a vector field is by sketching in 2 dimensions, and sketching in 3 dimensions is really just going to be a mess. Nobody can do that. All right. Remember that vector fields are vectors, and so all of the things that we could do to vectors, we can do to vector fields. For example, we can do dot products of vector fields, cross products of vector fields. We can normalize vector fields by dividing by the magnitude, which is what's going on here in the case of a unit vector field. So all of those vector operations, scalar multiplication, addition, they're all still on the table here. It's just now they're functions instead of constant vectors. So then here we have vector fields in 3D and sketching vector fields in 3D. We're not doing that. Gradient fields. So this is an important area. As I mentioned, a gradient field is one that is constructed by taking the gradient of some scalar function f. Remember that the gradient of f is the partial of f with respect to x in the I component, and the partial of f with respect to y in the j component, and additionally maybe the partial of f with respect to z in the k component in the case of 3 dimensions. These are vector fields, and they're very special vector fields. Not all vector fields are the gradient of some function. Only certain kinds of vector fields are. And in fact, they're so important that they actually have a name. They're called conservative fields. If a vector field is actually constructed as the gradient of a scalar function f, that vector field is called conservative. You can build the gradient field just by taking the gradient and you're done, so I'm not going to belabor that point. Here's a little bit more sketching of gradient vector fields. There are some really interesting geometric relationships hiding in sketches of gradient vector fields. We don't see that here, but in a minute, so here's this gradient vector field. What the authors have done is overlaid some level curves on top of that gradient vector field. So here is just the gradient vector field. Here is the gradient vector field with the level curves of little f, right? Little f here, superimposed. And an amazing thing happens. If you take the level curves of the function f, little f, and you superimpose the gradient vector field, you'll see that at every point in the plane, the vector field is perpendicular to the level curves. This is a really powerful geometric idea, and we'll talk a lot more about it in future sections. So now the big takeaway, a gradient vector field is perpendicular to the level curves of its potential function. What's the potential function? It's the little f that you took the gradient of to get the vector field. Little f is the potential function, big F is the gradient vector field. Verifying a potential function is really just taking the gradient and making sure that it matches up with the vector field. Let's see, what else? It turns out that potential functions are unique up to a constant, and you're going to see that if f is a conservative vector field, then we know that there's some potential function f such that the gradient of f is equal to the vector field. Is that the only f? No, in fact, if there is another potential function g, what we can say is that they differ by a constant, and this is very similar to the antiderivative of a function in Calc 2. In many, many ways, the potential function is the antiderivative of the vector field. I'm just going to leave that there, and we'll talk about it later. But remember, in Calc 2, antiderivatives differed by a constant. Whenever we antidifferentiate, we add that undetermined constant. Same thing happens here. Potential functions can differ by a constant. All right. Now, there's actually a really beautiful little test of conservativeness. Actually, it's not a test of conservativeness quite. It's a test of non-conservativeness. Let me clarify. If f is a vector field in 2 or 3 dimensions, if f is conservative, then the partial of the first component with respect to y equals the partial of the second component with respect to x. This equation must be satisfied. If f is a conservative vector field, this equation of partial derivatives must be satisfied. This is kind of a test for conservativeness in the sense that if this equation fails, then this is not a conservative vector field. The downside is if this equation is true, this might not be a conservative vector field. 99 times out of 100 it is, but there are a few exceptions which we'll talk about later. And in fact, there's a similar test for three-dimensional vector fields. If f is a three-dimensional vector field, p, q, and r, then these three partial differential equations are satisfied. I won't read it out to you, you can see that. If any one of these fails, then f is not conservative. The proof here relies on Clairaut's theorem about mixed partial derivatives. We know that if f is conservative, it's the gradient of some potential function f. That means that the first component of f is f sub x, and the second component of the vector field is f sub y. By Clairaut's theorem, we know that the mixed partials are equal. So if we take the partial of p with respect to y, that better equal the partial of q with respect to x, because behind the scenes, secretly, what you've done is mixed partials of the potential function. And we know that mixed partials are equal. Therefore, these first partials have to be equal. So everything really relies on Clairaut's theorem. So as I said, this is a great test for showing that a vector field is not conservative. It's not so great for showing that a vector field is conservative. In fact, we can find counterexamples. However, with a few very light restrictions, it actually can be used to show that a vector field is conservative, but we'll talk about that in a later section. Okay, let's jump over to the exercises here. I'm not going to do too many of them. A lot of them are review. For example, determine whether these are true or false. That one's pretty straightforward. Here you're asked to describe each vector field by drawing some of its vectors. I'm going to do number 6 here, and we'll talk a little bit about it. Find the gradient vector field for each function f. That's just really a review of taking the gradient of functions, which you did a while back. Here is a description of vector fields, and we'll build a vector field based on its description. And then last, we'll talk about flow lines, which are a pretty cool little side idea about vector fields. So without further ado, let's look at number 6. All right, in problem 6, we are asked to draw by hand or sketch some of these vectors by hand. Boy, this is a ridiculously confusing process, and I would encourage you to kind of at least do this once or twice just to get, I think it helps you kind of really get a grip on what a vector field is. The idea that a vector field is a function that assigns a vector to every point in space. That said, there are no easy ways of plotting these things. You just have to go point by point like you did back in maybe 8th grade. So we have a point, and I'm just going to go along and do sort of a few rows of points, and then we'll just call it quits. So let's do this blue segment here. That's going to be 1, 0, 2, 0, 3, 0, and 4, 0. And we're going to plug those into the vector field. All right, if I plug 1, 0 into the vector field, that means x is 1 and y is 0. So the resulting vector is 0, 1, right? Okay, the next vector, we can see a pattern here, 0, 2, 0, 3, and 0, 4, like that. All right, let's sketch these things. Now, the scale is up to you. I'm going to just use the same scale as the grid here, but scale is really a big issue when you're visualizing vector fields. You might want to really shrink the scale down or really blow it up depending on the magnitudes of the vectors that are in play here. So let's do these guys. So at the point 1, 0 here, there is a vector that points in the that is of length that is 0, 1. So it goes like this: nothing in the x direction, 1 unit in the y direction. Here, 0, 2. Here, 0, 3. Here, 0, 4. So those are the vectors that are attached to that first row of points. Let's build another row of points, a green row. All right, the green row is going to be 1, 1, 1, 2, 1, 3, 1, and 4, 1. All right, so let's work through that. We know that the first coordinate in each case is going to be -1 because that's y is 1. And the second component is just the x coordinate, 1, 2, 3, 4. All right, and let's plot those. So at the point 1, 1, we have a vector that goes -1 up +1. So that vector there. At the point 2, 1, we have a vector that goes -1 and up 2. At the point 3, 1, we have a vector that goes -1 and up 3. And finally, at the point 4, 1, we have a vector that goes -1 and up 4. All right, I'll do one more and then I'm going to call it quits. Let's do another row here. So the red row looks like this: 1, 2, 2, 2, 3, 2, and 4, 2. You really have to be organized when you're doing these. And that's going to yield -2s all the way down. And then the x coordinate, 1, 2, 3, 4. All right, so let's do the red dots now. At 1, 2, we go 2 in the x and 1 in the y direction for a vector that looks like this. At 2, 2, we go 2 in the x, in the negative x direction, and 2 in the negative y direction, or sorry, 2 in the y direction, like that. Okay, 3, 2, we're going to go -2 and up 3. Getting really messy here now, which is why it's hard to sketch these things. And then finally 2 over and up 4. Like that. You can kind of imagine that maybe there's a circular flow like this. You'd have to sketch more vectors to really see it. Fortunately for us, Sage actually allows us to plot vector fields relatively easy. Let me hop over to Sage and show you that. I would show you GeoGebra, but GeoGebra does not do vector fields very well. We're sort of almost at the limits of what GeoGebra will do for us at this point. Honestly, this is exercise 30. I haven't done, this is exercise 6. Let me see if I can just kind of wing it here. So we've got variables x and y, and that's probably good enough. And let's say the field, I'm going to guess that the field is going to be a vector field 2D, and then we remember that it's -y and x, and then we have to give it a range, and I'll just let x go from, say, -4 to 4, and y will go from -4 to 4, And there is, of course, no z component because this is a two-dimensional vector field. And then let's show the field when we're finished and cross our fingers. So plot vector field 2D is not defined. We have a solution for this. Plot vector field Sage. Just punch that into Google. Click on plotting vector fields, and there we go. It's plot vector field, not plot vector field 2D. So I'll get rid of that little 2D right there, and we'll hope for the best. And it's grinding away. There we go. And yeah, indeed, we do see this sort of circular field, this circular motion, which I was starting to kind of see. You can also see that the scale is different. So remember, there are two different scales when you look at a vector field. There's the scale of the lengths of vectors, and then there's the scale of the xy plane. And they are often two different things because as you see here, if you don't choose the scale carefully, the vectors really start to kind of overlap with each other, and it's really hard to kind of figure out what's going on. So a great trick is to just scale down the lengths of these vectors so that they're more visually pleasing, like this, for example. You know what? This is I think we can set the aspect ratio here too. To 1. And then that's a little bit better. This is it's not an elliptical sort of flow, it's actually a pretty circular flow. And we see that the magnitude of the flow gets large as we get away from the origin and is really small near the origin. Great. All right, let's look at another one here. So for the following exercise, we're going to write formulas for the vector fields that is described. So we want a vector field where all the vectors are of unit length and are perpendicular to the position vector at that point. So let me remind you what the position vector is and we're just assuming 2 dimensions here, although you could do this in 3 dimensions as well. So we'll assume 2D, so x and y. What's the position vector at that point? It's the vector whose tail is at the origin and whose head is at the coordinate x, y. So that's the position vector. What's a vector that's perpendicular to the position vector? Well, we have 2 choices. We have this one or this one. Let's switch the coordinates and change the sign on one of them. And if we do that, let's see, if we do that, we're looking at this one right here. So that's the choice we're going to make in this particular context. We have 2 choices. We chose that one. Now, that's not a unit vector in general. You can compute the length of this vector. Let's call this f. The magnitude of f is just, like always, the square root of the sum of the squares. And that's the square root of x squared plus y squared, and that's not generally going to be 1, right? If you're out here at, say, I don't know, 1, 3, right? What's the magnitude at 1, 3? The magnitude is 1 squared plus 3 squared, that's 10, square root of 10. So the magnitude there would be square root of 10, definitely not 1. How can we make sure that they're all of unit length? We can normalize. We can divide f by its magnitude. So doing that means dividing by the square root of x squared plus y squared, like that. And this is now a unit vector field. We can plot this one if you want in Sage, and you can see that it's a unit vector field. So if it's a unit vector field, we're not going to see this kind of variation in the magnitude of these vectors. What we should see is vectors that are all of the same length. So let's tweak this a little bit. I'm going to call this, in fact, I'll keep this here because I might post this. I'll keep this here and we'll just make a copy. And this is exercise 24. Okay, this vector field is normalized. Square root of x squared plus y squared, like that. And then this also dividing by the square root of x squared plus y squared. Might as well just keep this range and we'll just see what it looks like. All right, there we go. Now you see that all the vectors are perpendicular. Sorry, all the vectors are of unit length, and they are also perpendicular to any position vector. If you want to see that, let me make a copy of this. Control. So here's the full-on properly rendered sketch from Sage, and better give myself more space here. Okay. They're all of unit length, and if I take any position vector anywhere at all and draw this vector to the origin, you can see that these vectors are perpendicular anywhere at all. Right? Anywhere. So we've done what was asked, right? We've got all the vectors are of unit length and they're all perpendicular to the position vector. How did we do this? We started out with the position vector xy. We found a perpendicular vector, right? Yx, and changed the sign on the y. And then we normalized by dividing by the magnitude. All the things that you learned about vectors way back when, they're all still in play here. It's just now we've got variables kicking around instead of constants. Okay, the last topic is something called a flow line. And this is a very intuitive but also mathematically rigorous kind of thing. If I were, let's imagine this were some kind of whirlpool, and if I had a particle here and I sent it off in this direction, what would happen to it? It would flow around in this direction. It would flow along some natural trajectory. And that trajectory actually has a name. It's called a flow line for exactly this metaphor. And it's a curve such that the derivative of the curve is equal to the vector field along the curve. Got it? The derivative of the curve is equal to the vector field along the curve. So we're asked to verify that this curve is actually a flow line for this vector field. This really means that we need to compute both sides of this equation and show that they're equal. So computing the left-hand side of the equation means computing the derivative of c with respect to time. In that case, the derivative of the first component is 2e to the 2t. The derivative of the second component is 1 over t, and the derivative of the third component is minus 1 over t squared. So that's c prime. Now let's look at f of c of t. What does that even mean? It means take this component and put it in for x, take this component, put it in for y, take this component, put it in for z. Okay, so 2x. X is going to be e to the 2t, so it's 2 times e to the 2t, and that matches. Cool. Z. Take the z component and plug it in here. That's 1 over t. And finally, negative z squared. Take this and plug it in for z. Negative 1 over t squared. And they're equal, so check. This is a flow line. I've also used Sage to build a little visualization of this flow line. I'm going to plot this curve and I'm going to plot this vector field, and you're going to see how the curve kind of flows with the vector field. So that's actually the first exercise that I have up here. All right, here's the vector field. Now, deciding the ranges on x, y, and z are a little bit challenging, right? What I decided was, ultimately I'm gonna take this curve and I'm going to put it into the vector field. So I've got to decide on a range for this curve. And this curve is pretty problematic. It does not like 0. And furthermore, if I get too large, like if I take t equals 4 or t equals 5, you know, e to the 2 times 4, e to the 8th, that's a really big number. Not interested in seeing that at all. So what I ended up doing was looking at this curve on a very narrow interval, 1/2 to 1. 1/2 because it stays away from 0, where this blows up and this blows up, and 1 because that keeps e to the 2t relatively small. So now the question is, well, what's the vector field going to do, roughly speaking, over this range of parameters? Well, if in the first component, t is going from 1/2 to 1. So this is going to be between, say, 1 and e squared, which is on the order of 9. So I'm just going to keep, so this is going to be between, say, 1 and 9. I'm going to keep this just pretty narrow. Actually, there's an extra 2 in there, so I probably even should have thrown that in there. You get the idea, though. The y component, right, if the natural log of 1/2, that's going to be some small negative number, and then the natural log of 1 is 0. So I'm just going to use a really short negative range for y. And then z, if I'm going from 1/2 to 1, this is going to range from 1 to 2. So I used 1 to 2 here. So maybe my x range is a little bit off, but the y and z ranges, I can tweak the x range a little bit here. So this is going to go from, let's say, e to the first, so that's around 2, to e squared, which is around 9. So this is going to go from maybe 4 to 18. So let me tweak this a little bit. We can go maybe 4 to 18, like that. And then here's me plotting the vector field over that range, and then the flow over this range of parameters from 1/2 to 1. And we'll plot them on the same axes. So that means show the flow plus the field. And let me zoom in a little bit here. And it looks like I wildly overestimated my x range. In fact, let me cut the x range down a little bit. I can cut the x range down to, well, you know, it looks like maybe, you know, if that's 2 to 10, maybe 2 to 7, something like that. Let's try that. That's a little better. Okay. Now, it's really hard in 3D. You just kind of have to keep rotating it. But if you look down from above, you see that the flow line does sort of run tangent to these vectors in all of the right places. But you do have to look at it from a lot of different angles. But it's certainly believable that this blue line, which is the curve, is actually tangent to the vector field as it passes through. And that's what a flow line does. All right, so for suggested exercises, 5 through 14, sketching by hand in 2D, not killing yourself, but just getting the idea. Don't do any 3D. Sage is good for 3D. Problems 15 through 20, really just finding the gradient. And then in problem 29, I noticed there's a typo there. It should be r equals square root of x squared plus y squared. Once you've done a few problems and you've done your self-assessment, go ahead over the web work and try chapter 6, section 1. Good luck. Thanks.